Welcome to Lecture 16b, Triple Integrals in Spherical Coordinates. It's the second of three lectures on triple integrals in spherical coordinates. And here I'll work out some more complicated problems called Examples 1, and Lecture 16c will be Examples 2. The material for this lecture also comes from Section 16.5 of the text, and also Reading Assignment 2, reference material from Section 3.2, which is not mandatory reading. And so the objectives here are understand worked out examples from the textbook. Concepts and visualization skills are similar to the last lecture. The integration bounds for radius rho, angle phi, and angle theta. Visualization of bounding surface in spherical coordinates, and the differential volume in spherical coordinates. As usual, the second slide is just a summary of the remaining slides in this lecture, so we'll just move on. All right, so the first problem is a simple problem also. So what we'd like to do is evaluate this function integrated over volume, where D is a region in the first octant between two spheres of radius rho equals 1 and rho equals 2, centered at the origin. So if we were to draw that picture, then effectively what we would see is this being the octant. And so the ZX plane is one side, the ZY plane is the other side, and the XY plane is the bottom. And so we only see this portion of the domain, the total domain, and rho equals 1 would be the part that you see here, and rho equals 2 would be the outer surface that you see here. All right, so we also need to know what phi looks like, and we need to know what theta looks like. So if we look at this object, the angle phi is measured with respect to the z-axis. So that means we will be scanning from here to here, which means an angle range phi of pi over 2. And for theta, we measure from here to here, and so we're scanning an angle range of pi over 2 there as well. So we basically determined the range for theta, the range for phi, and the range for rho, and so we can actually compute the triple integral in spherical coordinates. So this is just an interactive demonstration you can look at if you wish. Otherwise, we just move on. All right, so spherical coordinate transformations, basically I've just restated them here. We now have to convert the integrand from Cartesian coordinates into spherical coordinates, so we can do that by direct substitution. You substitute for x, y, and z, and if you simplify, take the square, sum of the squares, this just becomes rho squared. And then you're taking the minus 3 halves power, so this becomes rho to the minus 3. From the previous slide, we know the range on rho, we know the range on phi, and we know the range of theta. And so we can set up the triple integral. So this integral now just in spherical coordinates just becomes, here's the integrand, here's the differential volume associated with spherical coordinates, and here are the bounds on rho, psi, and theta. And so if you simplify the first two terms, this just becomes rho to the minus 1. First we integrate with respect to rho, and then holding phi and theta constant. Then we integrate with respect to phi, holding theta constant. And finally, we integrate with respect to phi. In this case, the answer just is pi ln 2 over 2. All right, let's take a second problem. Find the volume of the solid region D that lies inside the cone phi equals pi over 6 and inside the sphere rho equals 4. So if I were to draw a picture of that, I would basically have a sphere. This is rho equals 4. And cone of psi equals pi by 6. Again, psi is taken an angle with respect to z-axis, so this would be pi 6. Theta, of course, can be anything from 0 to 2 pi. So all we're doing is doing a full rotation, and we're mapping out this cone. The top of the cone basically is the surface of the sphere. Okay, so rho will vary from 0 to 4. Theta will vary from 0 to 2 pi. And phi will range from 0 to pi over 6. So those would be the integration bounds that allow you to basically compute the domain here. The other thing is that if we're going to do a triple integral where we typically just say fxyz dv, then in this case, since we're dealing with a volume, fxyz will be 1 and has no units. And so that brings us to the next in the next after next slide. This is again just as an interactive version of what we just did on the previous slide. So you can look at it if you want to. All right, so here we go. We're basically using spherical coordinate transformation. And so, as I mentioned, we're interested in the volume. So fx, y, z is 1. It has no units. The domain we've already mentioned was rho between 0 and 4, phi between 0 and pi by 6, and theta between 0 and 2 pi. And so we make the substitutions. This is a simple integral. So there's the range for rho, this is the range for phi, and this is the range for theta. And so you just integrate with respect to rho, holding phi and theta constant. And then you integrate with respect to phi, holding theta constant. And then the last thing you do is integrate with respect to theta, and you end up with the final answer as shown here. The last problem is a little bit more complicated. They're being asked you is to write a triple integral in spherical coordinates to calculate the volume of a ball defined by x minus 1 squared plus y minus 1 squared plus z squared is less than or equal to 2. So if we draw a sketch of this problem, we'll notice that the center of the ball is located at 1, 1, 0. You know that because essentially x minus 1, y minus 1 tells you that the center has been displaced in the xy plane. And that the surface of the sphere passes through the origin. Well, how do you know that? Well, if you substitute x, y equals z equals 0 in here, then effectively you end up with 2 is less than or equal to 2. And also, we basically know, because it's symmetric, that the xy plane bisects the sphere. And lastly, that the plane y plus x equals 0 is tangent to the sphere at the origin. So this is the plane y plus x equals 0. Here's the sphere. And if you want to look at this and rotate it, then you can more or less click on this link and get a interactive version for this problem. All right, so let's solve the problem. So again, we have our transformation equations here for x, y, and z. So first thing is determine the boundaries on rho. So the bounds on rho are obtained by plugging in the spherical coordinate transformations into this equation and simplifying. If you do that, you'll end up with an equation rho equals 2 times cos theta plus sine theta sine phi. And the bounds on rho will be 0 at the bottom end. It can't go lower than 0. Less than equal to rho, less than equal to 2 cos theta sine theta times sine phi. So the next question is, what are the boundaries of theta and phi? All right, so this one requires a little bit of an intuition. What we want to do is to look at this function, and we want to basically scan all possible values of theta, followed by all possible values of phi, where effectively we're looking at the range of either theta or phi that takes rho from 0 to 0. In other words, the full scope. All right, so for instance, if we look at this situation here, all right, we'll find that if you take theta equals minus pi over 4, you'll end up with a 0. If you take theta equals 3 pi over 4, you'll end up with a 0. So everything in this range result in a rho which is positive, which it needs to be because rho has to be greater than or equal to 0. So that's the range for theta. Similarly, if you look at phi, you look at the range for which you go from 0 to 0. Well, clearly sine of 0 would be a 0, and sine of pi would be 0. Every value of psi between 0 and pi gives you a rho that's greater than or equal to 1. So these are going to be the limits or the bounds of integration for theta and phi. And for rho, we already have the expression for rho upper bound and for rho lower bound at 0. So this is effectively the integral that we want to compute. And the differential volume in spherical coordinates is just the expression that you see here. So we didn't bother in this case to actually solve the integral. The issue here was to set it up. If you wanted to go ahead and integrate this function, you certainly could. In this case, basically with d rho, when you integrate this, this will just become rho cubed over 3, and then between an upper bound and lower bound, rho cubed. And then you'd have to integrate with respect to theta, then followed by d phi. So you can do it as an exercise, but the point here was just to know how to set the integral up in spherical coordinates. All right, so that concludes lecture 16b. Thank you for listening.